So here are some example problems on starting on slide 20. Okay, so write the expression for the acid dissociation constant for nitrous acid. Okay, and actually that should say not dissociation, but ionization. Okay, basically, so we write out our formula. What do we have? So nitrous acid, HNO2. Okay, for all of these, we're going to be adding water, so plus H2O. We're double-sided arrows, and it's going to produce hydronium and the conjugate base, so NO2 minus equals. Okay, so that is our balanced equation. Now to write our expression, so the Ka is equal to the concentration of hydronium, so always products, okay, times the conjugate base, so nitrite, divided by the reactants. Again, water is a pure liquid. Its concentration doesn't change, so we don't include it. So this would be our expression here for nitrous acid. Okay, now, is nitrous acid a weaker or stronger acid than carbonic acid, and why? So for this, we just look in our data booklet. Okay, so nitrous acid is here. Okay, it's above carbonic acid, which is down here. So is it a stronger? Yes, it is. Okay, and why? It's got a, I guess the best way to explain it, it has a higher Ka. Okay, if we look at the Ka for nitrous acid, 5.6 times 10 to the minus 4. For carbonic acid, 4.5 times 10 to the minus 7. So why it has a higher Ka, which means it's going to make more hydronium. The next examples here. So consider the following acids and their dissociation constants. Okay, so we are given, or again, this should be ionization there. I gotta fix that. But okay, so we're given H2SO3. Again, it's Ka 1.2 times 10. This should be up here, but to the minus 2. And HS minus, okay, and 1.3 times 10 to the 19. So which is the stronger acid? Okay, it's whichever one has a larger Ka. So in this case, H2SO3 has a way larger Ka than HS minus. Okay, what is the conjugate base, okay, of H2SO3? So this is our conjugate base, whatever it produces as a product. So it looked like that. Which acid has a stronger conjugate base? So for that one, the weaker acid has a stronger conjugate base. So the acid that has a stronger conjugate base would be the HS minus. Okay, and which acid has the weaker conjugate base? Well, obviously, if we know one's stronger, then the other acid would be weaker. And which acid produces more ions? Basically, again, we look here. This one, 10 to the minus 2, it still favors reactants, but it's going to produce a lot more of the products than 10 to the minus 19, which really isn't going to make any products. So the first one is going to produce more ions. Okay, for this next example, we have propanoic acid. It's a weak monoprotic acid that is used to inhibit mold formation in bread. Student prepares 0.1 moles. Solution of propanoic acid is found to have a pH, okay, of 2.96. What is the acid ionization constant for propanoic acid? What is the percentage of molecules were ionized in the solution? Okay, so this one kind of plans out our strategy and stuff, and then we'll follow it. But so first off, we want to find Ka, so the percent ionization for propanoic acid. We're given the initial concentration of our acid. We're also given the pH, which, remember, the pH gives us the concentration of hydronium at equilibrium. So from that, then we have something at initial, we have something final, or at equilibrium. So then from there we can solve for X. Okay, so kind of planning our strategy. So we always want to write the equation for ionization equilibrium of propanoic acid and water. So that's where we always start, write down our balance reaction. Okay, and then we're going to set up our ice table. Okay, so we have balanced the equation here. Okay, for pretty much all of these, it's going to be a 1-to-1-to-1 ratio. Okay, again, for water, we don't worry about that because the concentration doesn't change because it's a liquid. Okay, if we have water as a gas, then the concentration changes and then we have to include it. Okay, and then just this, again, square brackets mean concentration, so the concentration moles per liter and so on. Okay, so our initial concentration, 0.10. And because I wrote moles per liter up here, I don't have to worry about writing it beside it here. Okay, again, these concentrations both start at 0. They're both going to go up by the value of x because they both have 1s as their coefficients. This will go down by the value of x because it has 1 of its coefficients. Okay, and so this is going to be 0.10 minus x. Okay, and then these are just going to be x. Okay, so that we set up our ice table, okay, and we also have our balance equations. Step 1's done. Okay, step 2, write the expression for acid ionization constant. So Ka is equal to the concentration of hydronium times our conjugate base divided by our initial weak acid. Okay, so that's our expression for acid ionization constant. Now we're going to solve for like x in our table here. So because we're given the pH, we can use the pH to then solve for our hydronium constant, or our hydronium concentration. So our hydronium concentration is equal to 10 to the minus pH. So 10 to the minus, we're going to go 2.96. So our concentration of hydronium is equal to 0.001, and like for significant digits, we have 2 after the decimal place, so it would be 1. Okay, moles per liter. Okay, so that's our concentration of hydronium, which is equal to x. Okay, because these are both x, okay, we know that like both of these, this is 0.0011. This is also 0.0011. Okay, again, this is a rounded number. I want to use my calculated number when I put it into here. Okay, to find my equilibrium here, so I got 0.1 minus x, so minus the value I just found. Okay, so I got 0.099. Okay, now I have all my values at equilibrium, so I can put them into my I can put them into my Ka expression. Okay, so we got hydronium, so 0.0011. These are both the same, so I'll just square that. Okay, and then divided by our initial 0.099. So our Ka is equal to we have 2 significant digits, so 1.2 times 10 to the minus 5. Okay, and then it also wants our percent ionization. Okay, so percent ionization is equal to our hydronium concentration divided by our initial concentration of our acid, so Ha times 1,000 or 100%. Okay, that gets our percentage. So in this case, we just put our numbers in. So hydronium 0.011 divided by 0.099 times 100% equals, and we get 1.1% ionization. Okay, so again, I skipped a couple pages. All of those examples are straight out of your textbook. Just go in there. I went through what page they're on. It's in your other set of notes saying what page they're on. But we're going to continue on doing these 2 more examples, and then I think that'll be it for this video. Okay, again, if you want more, just let me know and I'll do more. Okay, so this example here, we're given the hydronium concentration in a 0.1 mole per liter propanoic acid. Okay, is determined from the pH to be 1.16 times 10 to the minus 3 moles per liter. Okay, calculate the percent ionization reaction for this. So again, percent ionization is equal to the hydronium concentration, 1.16 times 10 to the minus 3, divided by our weak acid concentration, and then times 100%. So our percent ionization equals, so this equals 1.16%. Okay, calculate the Ka for the aqueous propanoic acid. Okay, so for this one, start by writing our balanced equation. So propanoic acid, CH3, CH2, COOH plus water, and that's going to produce hydronium plus our conjugate base, CH3, CH2, COO minus. Okay, and actually this example that we're doing right now is the exact same as the last example I just did. We even found this basically the exact same percentage. Okay, this is we'd write our ice table. This would be 0.1. Okay, this would be our concentration of both of these at equilibrium. We go this minus this would give equilibrium. We put in our Ka formula and go from there. Okay, so I'm going to skip through that one because we just did it. Okay, I'll do this next one here. Okay, so for this one, we have 0.1 solution of lactic acid, okay, which is a weak acid found in milk. It has a pH of 2.43. Find the percent reaction of this lactic acid in solution. So again, percent. So we need to solve for our hydronium concentration, I guess, first, which is equal to 10 to the negative 2.43. Okay, so our hydronium concentration, 0.0037 moles per liter. Now we can put that number in here, 0.0037 moles per liter, divided by 0.10 moles per liter, times 100%. And so we get 3.7%. Okay, and then the Ka value for lactic acid. So we don't know what lactic acid is. We don't know its formula. So for any of these ones, if we don't know, we can always just use the general formula HA, our weak acid, okay, plus H2O. And that's always going to produce H3O plus our conjugate base HA. So even though we don't know what this acid is, okay, we could look it up, or we could just use this general formula because it's always going to be the same as this anyway. Okay, we write out our ice table. Okay, because we're given this is the initial solution, this is the concentration at equilibrium. Okay, so this would be our 0.10 minus x, 0.10 minus x. We don't worry about this. These start at 0. They're both going to be plus x. And then, so this would be x and x. We know that this is equal to 0.0037. So this would also be equal to 0.0037. And then this would equal 0.10 minus 0.0037. Okay, so we solve for this, then put into our Ka formula, okay, and get our answer. Our Ka is equal to we have 2 significant digits, so 1.4 times 10 to the minus 4. All right, the last example here. I know this video is getting a little long. Nice thing about these videos, just skip forward to the example that is relevant to the question you're doing right at that time. Okay, so methanoic acid, which is HCOOH, is present in a sting of certain ants. What is the pH of 0.25 mole per liter solution of methanoic acid? So remember, like, we can find the pH only from the concentration of hydronium. So we have to solve for the concentration of hydronium. Any of these start with the ionization reaction. So we have methanoic acid, okay, plus water, and it's going to produce hydronium plus our conjugate base, so HCOO minus. Okay, we have the Ka for this. This is in our text or in our data booklet. We just look it up. 1.8 times 10 to the minus 4. Okay, and so if we have the Ka, write it down. Oh, it's out of my. Oh, I'm moving. There we go. Okay, so if we aren't sure where to start, always start with an ICE table if you don't know. It'll just kind of help you organize what you have and what you don't know and go from there. Okay, sometimes you won't end up using it. Doesn't matter. Okay, it's just a helpful tool to kind of get you started. So we don't need that. Okay, so we have so our solute, so we have 0.25 moles per liter solution of formic acid or methanoic acid. Okay, these will both start at 0. Okay, this would be minus x, or sorry, plus x, and then this would be x, and both of those. This is going to be minus x, so 0.25 moles per liter minus x. Okay, so now we put into our Ka expression. So Ka is equal to hydronium times our conjugate base divided by our initial weak acid. Okay, so that's the expression. So if we put these values in here, so we have 1.8 times 10 to the minus 4 is equal to, it'd be x squared on top over 0.25 minus x. Okay, for this one, like, now I have to bring this up. It's going to give me a fairly complicated one. So because of this, one thing I forgot to do is to check using the rule of 1,000. So again, the rule of 1,000, I take my initial concentration and divide it by my Ka, so 1.8 times 10 to the minus 4. Okay, and in this case, it's greater than 1,000, which means that I can forget about this. Basically, my value, like the x value is so small that this is going to stay 0.25. Okay, because like even minus x is going to be small enough that even with significant digits, this is going to remain at 0.25. Okay, that makes it a lot easier. Now, like when I bring it up, I don't have to factor in like 1.8 times 0.25 and then 1.8 times x times minus 4 and so on. Just makes it a lot simpler. Okay, so now I'm going to rearrange this to solve for x. Okay, so I'm just going to times both sides by 0.25. Okay, this cancels over here, so I got x squared is equal to 0.25 times 1.8 times 10 to the minus 4. 4.5 times 10 to the minus 5. I'm going to square root both sides to get rid of this x squared. So x is equal to 0.0067 moles per liter. Okay, so that's going to, this equals my hydronium concentration. Okay, and this question's asking for the pH. Okay, again, pH is equal to the negative log of my hydronium concentration, so 0.0067. So my pH will equal 2 and for significant digits, I have 2, so that means I'm going to have 2 digits after the decimal. So 2.17 is my pH. All right, so again, just feel free to ask any questions. Let me know what you're struggling with. I will do some examples based on your assignment also.